right, welcome back. This should be the last video for this part of the chapter. This has to do sort of a specialized kind of application of empirical formulas to hydrated salts. Now, I know we've already kind of mentioned this sort of briefly in passing in terms of what hydrated salts are and why we care about them, because all salts matter, right? But it's sort of a unique little kind of riff on what empirical formulas are. So with these, we'll talk about kind of what a hydrated salt is, kind of like in general how we write the formulas and all that stuff, and then how we apply that empirical formula problem type in a slightly different way to dealing with hydrated salts. Now, normally if we were in person, this is definitely one of the big labs that we typically do is determining the empirical formula of hydrated salts. So with this one, you can kind of see on the board, on the screen, there's an example of two samples of the same salt. These are both copper 2 sulfate. And what you can see in the top one is the pentahydrate version. It's a beautiful blue color. It's absolutely like gorgeous Lake Tahoe blue. And then the bottom one, which you can kind of see, is what happens to this pentahydrate salt as you start to heat it up. This one is used a lot of times because this one has a really strong color change. But something about having those water molecules in there, if you heat it up, you can kind of see it almost looks like it's starting to melt. And the water is getting driven off as water vapor. The remaining salt that's left behind is actually a different color. It's white. Something about having those water molecules associated with the crystalline structure gives it that beautiful, vibrant blue color. It's not that water is blue. Hydrated salts can be a whole bunch of different colors. But in this particular case, oftentimes this is used as the classic example because there is such a big difference. So with this, kind of what's going on? Well, when salts or when ionic compounds, salts, crystallize, a lot of times water molecules get sort of trapped in the matrix, trapped in the crystalline structure. It is called the water of crystallization, or the vapor of crystallization. There's names for this, but they sort of get loosely associated. And so in the top left diagram that's up there, kind of up on this part of the screen, you can kind of see our copper sulfate is here in the middle, where there's your sulfate over here, there's your copper atom right there, and these three water molecules are attracted to that copper for a variety of reasons, mostly because of polarity, partial charge. The copper is a pretty strong ion, and the oxygens have the sort of residual negative charge to them, a polarity to them. And so they sort of get acquainted with the copper, so to speak. And as these copper 2 sulfates form this crazy crystal lattice structure, these water molecules get stuck in there, and every particular time they form, there's gaps. And this is, I know it's hard to see, but in this particular thing where you're showing all of this lattice structure, you can see there's actually a decent amount of room in between all of these molecules for waters to get trapped. So again, I'm not going to ask you a ton of questions or anything about this, but just to kind of see where this is coming from. This sort of repeat structure, there's gaps in the middle, and these water molecules sort of sneak in there and then get trapped as it crystallizes. So you can kind of see I've got some examples of some fairly commonly used hydrates on here, and you can kind of get a view for how we write them. So this one right here is that copper sulfate that we've been working with. Let me get this out of the way so I can get my pen, pardon me. This one right here is the copper 2 sulfate. It turns out that copper 2 sulfate has, whenever it kind of freezes up, 5 water molecules. There's these 3 plus 2 additional ones that are not shown in this single, but are shown down in this diagram down below. Don't worry about it. But it turns out to be 5 water molecules for every single molecule formula unit of copper 2 sulfate. There are 5 of these. So we call that one a pentahydrate. Notice how they write it. There's a dot in the middle. It's a bullet. And then we put a coefficient in, and then the H2O to tell how many water molecules there are. The dot here indicates that they are loosely attracted. See how there's kind of that dashed line in there? They're not permanently bonded in there, and they're pretty easy to drive off. All I have to do to drive those water molecules off is use a Bunsen burner, and that water will turn into water vapor, and they'll just kind of yeet on out of there. So we've got barium chloride. This would be a dihydrate. Cobalt 2 chloride. This is a hexahydrate. Magnesium sulfate is a heptahydrate. This is actually bath salts, or Epsom salts is what that's called. And then sodium carbonate is a decahydrate. This is actually called cooking soda or washing soda, and it's closely related to baking soda, but that's what this particular thing is. So again, you can have a variety of different numbers in there, but again, you would just name it as dihydrate, pentahydrate, trihydrate, tetrahydrate, hexahydrate, all the different kind of combinations. The naming is actually pretty straightforward on there. So what we've got is when we're working with these substances, we have to take that water into account. When we pour out a container of copper 2 sulfate, this has a substantial amount of water in it compared to this version of it, which is the dried version. So this word right here, anhydrous, anhydrous, is translated from the Latin as without water. An on the beginning of a word means not or without. So this means not hydrated. So copper chloride or copper 2 chloride anhydrous has a very different mass than copper 2 chloride hexahydrate because all of these waters have mass. So copper chloride, by the way, cobalt chloride. What am I saying? Copper. Nice. Good job, me. Cobalt chloride. Cobalt's pretty heavy. I got to find it. 58.93. 58.93. Put this on here, 93. So this guy, 58.93. Chlorides are 35.45 each. So the molar mass of cobalt 2 chloride is 58.93 plus 35.45 times 2. So the anhydrous mass, 129.83 grams per mole. Okay, fine, no problem. But if you take a look at this is a substantial amount of water. Now, this is the same, right? That's still that 129. But water weighs 18 grams per molecule. 1.01 times 2 plus 16.00 gives us a total mass of 18.02 for the water. And then there are 6 of them. 18.02 times 6 is 108 grams of water. That's not ignorable. That's a lot of water, right? 18.02 times 6, 108 grams. So this total mass now, again, times 6 equals 108.12. The hydrate's molar mass is the mass of the water plus the mass of the anhydrous salt, 129.83 plus 108.12. Quite a bit heavier. This is 237.95. There's a substantial difference. It's not always a real big difference, but I wanted to pick one to really point that out. Grams per mole. That when you are calculating molar masses of stuff in a lab, you need to know whether it's the hydrated version, in this case it's got 5 water molecules in it, or whether it's the anhydrous version, which would have substantially less mass to it. So again, calculating the molar mass isn't that hard. You just have to remember to put the water in there and count it as well, because you can't just ignore it. So when we are doing materials with this, the one thing that we typically do, our lab that we do, is we try to figure out what the hydrate is. So imagine I gave you a sample of this lovely dark blue stuff, and I had you heat it up and turn it into this anhydrous version. And I said, okay, well, what was the formula? What was this hydrate? Is this a dihydrate? Is it a trihydrate? Is it a hexahydrate? Which one is it? That's the typical lab question that we typically do. So what we do is we take our hydrated salt and we heat it up massively. We don't want to burn it, but we want to make sure that all of that water is vaporized. And when we vaporize it, we're going to get a loss of mass, right? If these were the exact same amount before and after, whatever the change in mass was, whatever that is, would have to be equal to the water lost. That's the key idea that we're doing. You have the hydrated mass, you heat it up really, really, really strongly to make sure all of the water is driven out. And then you have afterwards the anhydrous mass, and you can compare the two. So here's what this looks like when we do the math on that. So you heat up 25 grams of hydrated copper 2 sulfate. After repeated heating, the anhydrous salt weighs 17.2 grams. What's the empirical formula of the hydrate? So we got to do a couple of things. We need our molar masses. But then the nice thing is when we are doing empirical formula of the hydrate, we do not need to know every single element. I know what the empirical formula of copper 2 sulfate is. I'm giving it to you. CuSO4. I'm telling you that formula. What I'm trying to find is this value, H2O. This is the only piece that I need. So when I'm doing empirical formula here, what I'm going to actually end up doing is moles of the salt, which is the copper sulfate, versus the moles of H2O, of water. And if I do just those two pieces, not every individual element, this is how I can get the the mass of my, the formula of my hydrated salt. So we got to start off by figuring this out. Okay, the 17.2. This 17.2 right here is the mass of our anhydrous salt. This is important because this is the one that does not have any water in it. So if I say 17.2 grams of CuSO4, I'm correct. If I say 25 grams of CuSO4, I am definitely not correct because this is 25 grams of CuSO4 plus some random amount of water that I don't know what it is. So make sure, step number one, is that you're always using your anhydrous mass so that you know that that really is just the copper sulfate, whatever your salt is. And then I got to do my grams to moles conversion. Grams to moles. Let me figure out what my molar mass of copper 2 sulfate is. Copper has a mass of 63.55. Sulfur is 32.07. And then oxygen is 16 times 4, right? Because it's sulfate. So our molar mass of copper 2 sulfate is 159.62. And again, that's 1 copper, 63 grams-ish, 1 sulfur at 32 grams, and then 4 oxygens at 16 grams each. So that's 1 mole. So 17.2 divided by 159.62 equals, oops, 117. Again, my stupid number 6 does not work. Divided by 159.62. There we go. And I get this value, 0.108 moles of that stuff. So now, again, rather than doing it element by element, we're doing it salt versus water. So what I need to do down here in my second one is this is going to be where I'm going to analyze the water content that's in here. Now, I don't have that value directly, right? This number up here is my hydrated. That's salt plus water. This 17.2 is salt only. So in order to figure out the mass of the water, it's the change in mass. That water vapor was let out as steam and it ran away, and we don't have it there directly anymore, so we can't measure it, but we can measure it indirectly simply by subtracting. So 25 grams of salt plus water minus 17.2 grams of salt gives us a remaining mass of 7.8 grams. And again, we're trying to find the delta mass in order to figure the H2O. That's what we're looking for. So it's going to be the 25.0 minus 17.2. That's what we were doing. All right. Now we got to convert this one to moles as well. Grams of H2O to moles of H2O. Off the top of my head, I happen to remember that water weighs 18.02. We use this a lot. 16 grams for the oxygen plus 1.01 for each hydrogen that's on there. So now when I do this one, how many moles of water did I lose? Just like in the other empirical formulas, you have to do this in moles. So that's what we are doing this conversion. 18.02 gives us 0.433 moles. Again, I don't have to worry about sig vig so much because this is not a final answer. So this means I had 0.108 moles of salt and 0.433 moles of water. So now what I need to do is, just like in our other empirical formulas, I want to simplify that ratio. And I want to see what the ratio is. You can probably kind of tell by looking at it. But 1.108 divided by 0.108 is 1. It's always going to be 1 for the salt. 0.433 divided by, 0.433 divided by 0.108 gives me a value of 4.008. So close enough to 4 that I can feel pretty good about rounding it. So this isn't the real value of copper 2 sulfate. I just made one up so we could have one to work with. So this tells me now this is the salt and this is now the water. Again, it's just like empirical formula problems, but now instead of doing every individual element and doing a subscript number, now what we're doing is doing the salt versus the water. And this tells us that it is CuSO4, there's our salt, and then we use our dot because it's a hydrate, 4 waters, 4H2O. It's a tetrahydrate. It's really a pentahydrate, but for this particular lab, we're calling it a tetrahydrate. So that's how you do empirical formulas for hydrates. And I hope that we can actually get to do this in a real lab because it's actually kind of fun to heat up really toxic compounds and drive off the water. So there you go. Empirical formulas and how they relate to hydrated salts. That's the end of this particular section and the end of this particular part of the homework. Good luck. See you guys in class. Bye.